Yeah, I think that's under. I think it is.
And now that's
Okay. So, you're working on the next problem set, you've got the new problem set. Okay, we're just going to continue today. I'm ready to finally prove something we've been using for weeks now, the equal partition theorem. Okay. Finally, we're going to validate that, which we've just been stating, okay, without proof. So, that's what we'll start with today. I believe we're up to 7. Yes, tell me if I miscounted. Proving the equal partition theorem. It's quite an elegant little proof. And it all just boils down to Gaussian integrals. Okay? Okay. So first we better list what the necessary conditions are for the theorem to be valid. 1, the classical limit of the canonical partition function is valid. We have to be in the classical limit. We cannot be in the quantum limit. What does that mean in kind of practical terms? It means that the energy scale set by the temperature of the reservoir, kBT, which we've talked about a lot in the canonical formalism, right? That's the energy scale set by the temperature of the reservoir. That energy scale must be larger than any of the energy level spacings, the difference between adjacent energy levels, which I'll just denote delta E. So delta E refers to the largest of the energy level spacings. Okay? Because when the thermal energy scale, kBT, is large compared to the spacing between energy levels, then that means the spacing between energy levels is not going to be that important. Okay? Because thermal energy will be large enough to induce transitions over many different energy levels. Okay? And so one particular energy level is not important if you can induce transitions over many of them. And that's what this kind of limit is, or inequality is saying. Got enough thermal energy to induce transitions over any of a range of energy levels. Therefore, I don't really notice the discreteness of the energy levels so much. Right? Now, when that's not true, when the thermal energy scale is small compared to the energy level spacing, then you don't have enough thermal energy to boot yourself up to a higher level, and you tend to be stuck in one level, and you say, all I know is one level. That's quantum. That's quantum behavior. Okay? So that's what basically has to be true. So if you want, you can basically say this very loosely that, well, I've got to be at a high temperature limit. But this is what we mean by high temperature. Okay? Now, that's not the only necessary condition. The other is that the classical expression for the total energy of the system splits additively into 2 parts. One part that is quadratic in a single variable, right? For example, how about x position? That's going to be the variable I'm going to use as my example. Right? One part of the energy is quadratic in, say, an x coordinate. An example would be a harmonic oscillator oscillating along the x-axis. Its potential energy function is proportional to x squared, right? Elastic potential energy, 1/2 kx squared, where k is the spring constant. Okay? So, when you write down the classical expression for the total energy of this system, it's going to break up into two separate parts added together. One part is going to be quadratic in a single variable, and the other part is independent of that variable. So, for example, this part has to be independent of x, if x is my variable that's quadratic. So that would look something like this. I'm going to write the total energy like this. It's going to be the quadratic part, right? It's quadratic. I'm going to say an x, okay? And then there'll be the other part of the energy, which is not quadratic in anything, okay? There can be such energy terms that are not quadratic in a variable. And in fact, I'm going to list this as E other, and I'm just going to use a symbol P, maybe for example for momentum, that represents all the other variables that the energy might depend on, but in which the energy is not quadratic. That's what the other part means, not quadratic. Now, of course, there could be multiple parts to this. This could be further subdivided into a part that's quadratic in x and a part that's quadratic in another variable too. But let's just take one variable as being the quadratic one, okay? So the energy has to break up additively into two parts. A part that is quadratic and a part that isn't, okay? All right, now let's state the actual theorem. So let's state the equal partition theorem, and then we'll prove it. All right. Given conditions 1 and 2, the average value of the quadratic energy term, the average value of the quadratic energy term, E quad, is, as I hope you know, 1/2 kBt. Regardless of numerical constants in the expression E quad, regardless of numerical constants in the expression E quad, and independent of the details of that part of the energy we're calling E other. So the way we would write that is E quadratic thermal average bar on top is 1/2 kBt. So now we're going to go through proving this. Now this is what we have been using all along. And remember the way we talked about it earlier this semester is we stated the equal partition theorem slightly differently than this. We said for every degree of freedom that a system has, you get an average energy of 1/2 kBt for every degree of freedom. And then we said, well, then we've got to know how many degrees of freedom a system has. We can have a symbol for how many degrees of freedom a system has. Little f. And we had to be able to figure out how many degrees of freedom, what was the value of little f. And how did we do that? We said there's a degree of freedom is every part of the energy that goes like a coordinate or a momentum component squared. Quadratic. Okay? So we've been saying and using the partition theorem all along. We're now finally going to prove this part right here. And the fact that when you average the quadratic part of the energy, whatever this part is, doesn't matter. Okay? So that's what we're going to do. So, B. What I need now is I need, for condition number 1, the classical limit of the canonical partition function. So I need to talk about how we're going to think about that. Okay? So, the classical limit of the canonical partition. Let me start with what ought to be the safest starting point, the very definition of partition function that we've been using all along. Partition function, remember, in German stands for sum over states. So, I'm going to sum over all the states. What do I sum? The Boltzmann factor for each state. E to the minus beta times the total energy. Okay? Remember, beta is 1 over kBt. Okay, now let me start. That's my starting point. I know that's got to be a good starting point. That's the definition of partition function. Let me use the fact that my total energy for my system is broken up additively into 2 parts. A part that's quadratic in a variable, we're going to choose the quadratic variable to be x. And then every other part of the energy that's not quadratic. Okay? We'll say it depends on the variable p. It depends on multiple variables. So this is the sum over the states, e to the minus beta times e quad of x plus e other of every other variable, but I'm just going to represent that by p. Let's take e quad, depending upon the variable x, to just be a constant, little a, times x squared. It's got to be quadratic, so let's take it to be that form. Okay? I'm not going to make any other assumption about e other. Right? Because it's not a quadratic function of p. It could be anything that's not quadratic function of p. It could be linear in p, it could be p cubed, it could be log p, I don't care. Okay? Alright, let's just take that. Then the partition function is the sum over the states of e to the minus beta. Now I'm going to break up the Boltzmann factor into a product of 2 exponentials. There's e to the minus beta times the quadratic part, and then I'll multiply that by e to the minus beta times e other. Right? I can do that. Property of exponential function. It's going to help me a little bit now to figure out how I'm going to represent this sum. I'm supposed to sum over the states. Well, the Boltzmann factors depend on 2 variables in my proof here, x and p. So I'm going to sum over the states by summing over all the possible values of x and p. All the possible values of x and p. Where these sums are independent of each other. So it's actually 2 sums. There's a sum over x and a sum over p. So I'm going to write it like this. Okay? And, just for bookkeeping purposes, it's handy to think of this product right here, with one part being the sum over all possible values of x, e to the minus beta ax squared, I'm going to label that part the partition function that came from just the x dependence, z sub x. And then this is any other variable, even though I've labeled it p, but the idea for this is that it's anything else that the energy depends on, that it isn't quadratic. So I'm going to call this part of the partition function z other, from everything else. All right. Now, how am I supposed to think about summing over x values? Because we tend to think of x as being continuous. Okay? And maybe you can see where we're headed. We're ultimately going to end up with an integral over x. But we've got to get there. Let me show you what's the next step. So I'm going to focus on the zx. That's going to be the most important thing for now. Again, I'm trying to figure out how I'm going to sum over allowed values of x. Sum over x states. Well, let's think of the x-axis as being divided into many small intervals of size delta x. It's arbitrary. We'll imagine taking the x-axis, there's 0, all the way from one limit to the other, whatever that might be for the given system, and dividing it up all the way down, dot, 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 where each little interval is size delta x. Now this is just a thought process right now, but I do want the delta x to be small enough that the energy, the part that depends on x, doesn't vary much when I go from one little interval to the next. So however small I have to pick delta x, so that the energy doesn't vary much when I go from one interval to the next, that's how small I'll pick delta x. You'll see in a minute that the actual size of delta x is not important. Okay? If I do that, though, imagine breaking up the x-axis into a whole bunch of little intervals, then I know what it means to sum over x. Because each interval has an x value. And so summing over x means summing over the x value at the center of each interval, working your way from one end to the other. Okay? So now what I'm going to do is I'm going to take the zx part of the partition function, and I'm going to multiply and divide zx by this little interval size, delta x. So then zx is 1 over delta x, sum over all the x values, Boltzmann factor, e to the minus beta ax squared times delta x. So I'm summing over all the possible x values, that one x value for each interval. What am I summing? Well, this product. The Boltzmann factor for each x value, e to the minus beta ax squared, times the size of that interval. I'm going to think of that product as an area. It's the area of a column in a bar graph, where the width of each bar is delta x, and the height is e to the minus beta ax squared. Right? Now the whole point about being in the classical limit is that the size of kBt is large enough that there will be many, many of these bars in the bar graph that contribute to that sum. Okay? So here's an important point. kBt must be large enough that many columns or bars, each of width delta x, contribute to this sum. Let me show you that. That's what we mean, by the way, by classical limit. Let me show you what I mean with an actual graph or plot. Power open up here. Okay, there we are. All right, now, what you'll see on this plot in the top is the following. I plotted x horizontally. What did I plot vertically? E to the minus beta ax squared, where I picked 1 over beta a to be 30. Right? Because KBT is 1 over beta. So this is 1 over beta times a. And I picked a number for that 30. Notice, since KBT is upstairs, a large number for this is basically saying high energy. Okay? And then I just arbitrarily divided up the x-axis into little bins of size delta x, and I made a bar graph, where each bin was width delta x, and the height of each bin, represented by the blue rectangles, is the value of e to the minus beta ax squared at that x location. And so you get this bar graph with all these blue rectangles. And then I just put a smooth Gaussian e to the minus beta ax squared right on top of it. That's the red curve. And for this high temperature, notice there are many rectangles that contribute. And that each rectangle is small compared to the overall width of the Gaussian. So it's not going to be bad approximation to say the total area of the blue rectangles is approximately the same as the area under the red curve, because so many rectangles will fit. And so I'm going to convert that to an integral over x. Now here's where you wouldn't have classical behavior, non-classical. I chose a value of 1 over beta times a to be a factor of 10 less than it was up here, so that you only have a few of your bars in your bar graph that have contributions, have area under them or in them. Right? And then if you only have a few of your rectangles that are important, converting the sum to an integral is a little bit more dicey. Okay? So the point is, we're thinking about a situation like this. Okay? And if we have a situation like that, where there are so many of these little rectangles, each with their own area here, contributing to this sum, I can just change that to an integral and that to a dx. And I'm not even going to touch that, I'm just going to leave it, 1 over delta x out front. As I said a moment ago, the delta x isn't going to matter. Okay? Okay, so with that picture at the top in mind, we now write z for the x coordinate as 1 over delta x integral. Let's say the entire x-axis is what's available to our system, so from negative infinity to infinity, of e to the minus beta ax squared dx. I told you the equipotential theorem is really all about Gaussian integrals. There's our first Gaussian, right? That is a famous Gaussian integral. In fact, we can just use the well-known result that the integral from minus infinity to infinity of e to the minus positive constant b times x squared dx is the square equal to the square root of pi over b. One of the most important integrals that physicists use, right? The Gaussian integral. Root pi, and then a b downstairs because of that multiplicative factor there. Okay? So if we use that, then what do we get for the partition function associated with the coordinate that was quadratic? Remember, the quadratic coordinate? We get 1 over delta x square root of pi over beta times a. Let's number that because we're going to need that. Okay? Now, with that kind of reasoning in hand, we've calculated the partition function associated with that variable which was quadratic. We can apply similar reasoning to get an expression, an integral expression, for the rest of the partition function. The part of the partition function that came from all the other variables in which the energy was not quadratic. That is to say, I will make the same assumption that we're in a classical limit, and that I can take this part, z other, and I can multiply and divide by an interval delta p, right? Break up the p variable into little intervals, and that this will then, there'll be a 1 over a delta p downstairs, and a delta p here multiplying upstairs, and I'll think of that right there, that product, as the area of a rectangle, and I'm adding up all the areas, but there'll be so many rectangles, I'll make it into an integral. Okay? And so when it comes time to calculate z other, there'll be a 1 over delta p, sum over the entire p axis, e to the minus beta times e other of p dp. And I can't do any more with this because I haven't specified exactly what this function e other is. Right? But the whole point of the equipartition theorem is that when you're averaging the part of the energy that's quadratic in a variable, then the details of this rest of the energy, e other, don't matter. So I shouldn't have to know what that is. I'll just leave it like that. We'll see what's going to happen with that in a minute. All right. Now, next thing. The whole point is to find the average value of that part of the energy that's quadratic, the E quad. So let's remind ourselves how we do averaging in the canonical formalism. Let's write down an expression for the average value for some generic quantity Q, let's say. The thermal average value of a generic quantity Q, Q bar, is sum over the states, I'll use a generic symbol S, the value of Q for state S times the probability of state S. Right? That's how we would find the average value of a quantity Q. In the canonical formalism, remember, we know what the probability function is in the canonical formalism. It's the Boltzmann factor for state S divided by the partition function. Okay? So that's 1 over z, we'll bring that out front, sum over the states S, the value of Q for state S, times the Boltzmann factor, e to the minus beta, energy total, function of S. I mean, that's how we find averages. Next thing, in the classical limit, just remember, sums become integrals. So let's show you how that's going to happen. Because what we want to calculate, of course, is, so step 2, what we want to calculate is the thermal average value for the quadratic part of the energy, E quad. Okay? So let's use this procedure that I've reminded you of. Right? Since this is a generic quantity Q, let's take Q to be E quad. So E quad average will be summing over the states. I'm not going to put the symbol S here now because I've just got to, this whole summing idea is you've got to have some way to sum over the states. And you've got to think about how you're going to label the states and all that. So I'm just going to put the sum there. E quadratic, which is a function of x, e to the minus beta times e total, which has the quadratic part is a function of x, and everything else, which is a function of p, all over the partition function, which remember, I've written as this product of zx and z other. So that's what it would mean to find the average value of E quad. Okay? Okay, so next step. Like I said, at the bottom of the board over there on the left, in the classical limit, sums become integrals. Sums become integrals. So, E quad average is, well, I'll do this in a couple of steps. I'll break that sum down into a sum over x, E quad of x, e to the minus beta times E quad of x, multiplied by another sum over the p values of, well, what's left in the numerator. I've already got that part and that Boltzmann factor. So what's left is just e to the minus beta e other of p. There's the numerator. Yes? Everybody see what I did? You see that that is the numerator from there. Just group things a little bit. What's in the denominator? Zx times z other. Okay? Now I'm going to use what I said over here. In the classical limit, sums become integrals. Now, be careful what that means. That means, remember, multiply and divide this term by a delta x. So you'll have a 1 over delta x in the front and a delta x right here. Then pass to the limit, and that becomes an integral, and that becomes a dx. This one, multiply and divide by a delta p. You'll have a 1 over delta p out front, you'll have a delta p here, pass to the limit, that'll become a dp, and that'll become an integral. I've already worked out zx. It's on the board. I've already got an integral version of z other. It's on the board. So everything's now going to be integrals. You ready? Here we go. E quadratic average is, okay, for the first term in the numerator, 1 over delta x, sum over the entire x-axis, minus infinity to infinity. Remember, E quad is constant a times x squared. And then times the Boltzmann factor for that. So e to the minus beta times a times x squared dx. Close parentheses. There's the first integral in the numerator. Next integral in the numerator. Remember, multiply and divide by delta p, so you get a 1 over delta p out front, and then the sum becomes an integral. Integrate over the entire p-axis. All you're integrating here is the Boltzmann factor, e to the minus beta e other of p dp. It's very important you understand why there's something multiplying the Boltzmann factor here and just a 1 multiplying the Boltzmann factor here. Do you understand that? Why I've written it that way and why that's correct? Very important. Okay? Multiplicative factor of an x squared multiplying this Gaussian, 1 multiplying this function. Now, what's in the denominator? Zx Just use equation 1 for that. Okay? So 1 over delta x, square root of pi over beta times a. Right? Equation 1, already worked out Cx. And then what else in the denominator? Oh, z other. Well, I've got an integral expression for z other, yes? So use that. Now looking over there, 1 over delta p, integral from negative infinity to infinity, e to the minus beta times e other of p dp. And now I see that the part in the numerator that came from the non-quadratic part, which is only multiplied here by a 1, when I write it here as an integral, turns out to be exactly the same as the z other in the denominator. And that therefore those cancel, and the energy E other is absolutely irrelevant. Absolutely irrelevant. And all I am left with to get E quad average is that integral divided by that. Okay? So, let's see what we get. Notice we have another integral in the family of Gaussian integrals in the numerator. Okay? Namely, it's the integral of a Gaussian function of x multiplied by x squared with a constant. So, let's get this as pretty as we can. E quad average is, well, notice something else. I told you the delta x isn't going to matter, right? Look, there's a 1 over delta x in the numerator and the denominator. The delta x, the details of the size of delta x are immaterial. Then this is downstairs, so when I take it upstairs, it becomes square root of beta a over pi. And there's an a right there in the integral, which is a multiplicative constant, so it can come out front of the integral. So do that. Then I have the integral from negative infinity to infinity, x squared e to the minus beta a x squared dx. Very famous integral right here. Very famous. Notice it's technically not just a Gaussian. It's a Gaussian of x times x squared. But it's easy to figure out that result. That is to say, Mathematica will tell you what this integral is. And that integral is 1/2 square root of pi over beta cubed times a cubed. So let's see what our final result for E quad average is. Square root of beta. Notice this a out front of the square root. Let's take it inside the square root. It'll become an a squared. Already multiplying an a in there, so that'll become an a cubed inside the square root. So that's what I have out front. And then that's multiplying from this integral 1/2 square root of pi over beta cubed a cubed. Now, a lot of things cancel. Pi, pi, a cubed, beta, beta cubed. So this is 1/2, 1 over the square root of beta squared, which is 1 over 2 beta, which is 1/2 kBt. Okay? The average energy from the part of the energy that was quadratic is 1/2 kBt. Note that when we wrote down the quadratic energy expression, it had a constant a times x squared. Notice the constant a, absolutely immaterial in terms of what the average energy is. Doesn't matter what that constant is. And it doesn't matter what the E other part of the energy is. In terms of calculating the average value of the quadratic part, 1/2 kBt. Yes?
There is still somewhere as a 1 constant at the very top for the B brother. Why it's 1 times the Boltzmann.
See here? Okay? I'm averaging E quad, so it's E quad times the Boltzmann factor with the total energy. I broke up this into two exponentials multiplied together. E to the minus beta e quad times e to the minus beta times e other. Right? There's the e to the minus beta e quad. There's the e to the minus beta e other. The e quad that's sitting right here goes with that exponential. And then there's just times 1 right there. That goes with that one. You can think of it that way. Okay? And it's because there's nothing other than a 1 here and here that this term in the numerator is exactly the same as z other. And they cancel, and then the calculation of e quad average doesn't depend on e other. Okay? So now we've proved it. The equal partition there. Okay? This is the kind of thing that you might be asked on a graduate school oral exam. Prove the equal partition theorem. All you got to do is say, oh, all I remember are Gaussian integrals. Everything's Gaussian, right? Because if the energy is quadratic, the Boltzmann factor is e to the minus beta times something squared, right? But e to the minus constant times variable squared is a Gaussian. So it all boils down to just, oh, okay, it's all Gaussian. Gaussian integrals. Maybe you say that to the professors and they might say, that's good enough. They might. Okay? All right. Now you can do some applications. I'm not going to go into great detail because we've done applications already, right? Like if I told you you have a harmonic oscillator and the temperature is high enough that you're in the classical limit. That means the energy level spacing for harmonic oscillator, which remember is h bar times omega. Omega is the angular frequency. That energy level spacing is small compared to kBt. And your oscillator's in the classical limit. What's the average energy? Your answer is? What? Total energy of a harmonic oscillator has how many quadratic parts? What is the energy? What is, oh, I think actually I'm going to have to write this out. Right? All right. Applications. An equal partition. Okay. How about a harmonic oscillator, right? What's that?
Is this a new letter?
I can't hear
Is this a new letter?
you. What was my last letter?
C.
Then yes, indeed. Remember the energy of a simple harmonic oscillator? Because we've got to start. The partition function requires you to have your Boltzmann factor, e to the minus beta times the total energy. So tell me what the energy is. The expression. No, start from physics 110 for me. Okay, start from physics 110. Rock on a spring, oscillating back and forth along an x-axis. 1/2 mv squared. Is that it? Plus what? 1/2 the spring constant, k. I'll use a capital K. I don't want you to think of Boltzmann's constant. X squared. Okay? Classical limit. Let's say you're in the classical limit. That means if I plot the energy levels, E of n, starting at 0 and going up, they're equally spaced, okay? So if n equals, this one is at h bar omega over 2. This one is at 3 h bar omega over 2. Up they go. The point is the spacing between adjacent ones is h bar times omega. Okay? And then if I plot on that same scale how big the thermal energy is, let's say it's that. It's kBT. Right? So that the thermal energy is large compared to the energy level spacing. Right? Depends on what's the temperature of the reservoir that the oscillator is in. Okay? But this is what's got to be happening. The thermal energy has got to be large compared to the energy level spacing. Then you're in the classical limit. Then you can apply the equipartition theorem. Understand? If you're in the low temperature limit of a harmonic oscillator, where the kBT is like this, then you're probably stuck down here in the ground state and you can't go anywhere, right? It's not the classical limit then. You can't use the equipartition theorem, just put it away. Can't do it. Okay? So assuming we're in the high temperature limit, the classical limit, and I ask, what's the thermal average energy of this oscillator? What would your answer for that be? The thermal average energy of this oscillator is. Okay, got a system. It's in a reservoir, temperature T. kBT is large compared to the energy level spacing. If I do a thermal average energy for this oscillator, what will I get? One half kBT is that the total? You get 1/2 kBT for every term in the energy that is quadratic. Yes? For every term in the energy that is quadratic, you get an average energy of 1/2 kBT. So, there's a quadratic term, so you get an average of 1/2 kBT from that, plus there's a quadratic term. So 1/2 kBT from that. So the final answer, kBT. Now, you shouldn't feel bad if you didn't know where I was going with that, because the same thing happened to us when I was in graduate school. I was taking a class in solid-state physics in graduate school, and the professor loved to ask undergraduate physics level type questions to try to trick us. Okay? And so he asked, what's the average energy of an oscillator? That's all he said. What's the average energy of an oscillator? We were going around like, well, you know, and nobody said kBT, and he got more and more irritated and angry, as none of us was saying. And then finally he had to tell us what he meant. And somebody tried to push back and said, well, you didn't make it clear. Oh, he went off. He just blew up. He wasn't having it. He was saying, if you're a physics graduate student and we ask you for the average energy of something, his thought was, you should go immediately to the equipartition theorem. I don't know, but that's what he had in his head. Okay? It is, however, important and very useful.
So do you just assume that it's in the classical limit unless there's reason to believe otherwise?
That's an interesting question. At the graduate level, I would tend to say yes. That's probably what they mean when they ask for the average energy. They probably mean for you to use equipartition. However, be aware, you can get burnt. If there's a situation where this isn't true, run from the equipartition theorem. Get away from it. Okay? But most of the time, if it's a quick and dirty question in graduate school, they mean for you to use the equipartition. Okay, now I have another one I want to do, but I think we'll take our break, and then we'll come back and apply the equipartition theorem to something a little different.